We are in Rosen, Discrete Mathematics and its Applications, section 10.7. We're continuing our discussion of Euler's formula and some corollaries for planar graphs. Here we look at corollary 1, where we say that if G is a connected planar simple graph with E edges and V vertices, as long as there are greater than or equal to 3 vertices, then we can say that the number of edges must be less than or equal to 3 times the number of vertices minus 6. Okay. We'll do our proof on the next slide, but it requires the concept of degrees of a region, which is the number of edges bordering the region, and we count any edges twice that lie within the region. So here's our illustration. Here we have a region 1 is a region of degree 3 because there are 3 edges bordering it. Region 2 will count the edges around it, 1, 2, 3, 4, 5, but then we have to count the other side of that edge to get back to our starting point, 6. And 6 is the degree of that region. Let's do the outside region. It also has a degree value, 1, 2, 3, 4, 5, 6, 7 to get back to where we started, and that's the degree of that region. All right, before we do the proof, let's make a quick application, and we want to show that K5 is not a planar graph. We'd shown earlier that K33 is non-planar. K5 is the graph with the complete graph with 5 vertices, and it looks like a pentagon with a star inside of it, like that. And it has 5 vertices and 10 edges. So we'll do the right-hand side of our formula from corollary 1. 3 times the number of vertices is 15 minus 6 is 9, but 9 is not greater than or equal to 10, so it cannot be a planar graph by corollary 1. All right, let's prove corollary 1. So proof of corollary 1. G is connected planar simple with vertices greater than or equal to 3. Let's see. One of the things we can say about this is since we have at least 3 vertices is that all regions must have a degree greater than or equal to 3. Since it's connected and I've got 3 vertices, there's no way I can have a region of degree 2. That could only occur with the graph K2 and connected graphs. So now we can also remember that if we count up all the regions, the degrees of all the regions, every edge is counted twice. So 2 times the number of edges is equal to the sum over all regions of the degrees of those regions. And since the degree of all those regions is greater than or equal to 3, that number will be greater than or equal to 3 times lowercase r, which is the number of regions that a planar representation of G divides the plane into. And I'll substitute Euler's formula for r here. So that says 2e is greater than or equal to 3 times e minus v plus 2. That's 2e is greater than or equal to 3e minus 3v plus 6. And I'll subtract sum from each side to get 3v minus 6 is greater than or equal to e, which is what corollary 1 asserts. Okay, we're going to use that in the proof of the next corollary, corollary 2. If I have G as a connected planar simple graph, and G has, then I can say that G has a vertex of degree not exceeding 5. All right, well, if I've got 1 or 2 vertices, then I certainly won't have degree, degree exceeding 5. I will have a degree less than or equal to 5, excuse me. And if I have 3 or greater vertices, I can apply corollary 1 and say, since I've got a CPS graph, that the number of edges is less than or equal to 3v minus 6. Now if I multiply both sides of that by 2, I get 2e is less than or equal to 6v minus 12. So I'm going to prove this by contradiction. I'll say that, let's say that it's possible to have all vertices 6 or greater. So if every vertex were at least 6, then because of the handshaking theorem, 2 times e would be greater than or equal to 6 times v. But that would be a contradiction to 2 times e being less than or equal to 6v minus 12. So by contradiction, we must have a vertex with degree no greater than 5. This will be a very important component of a theorem that we will prove in the next section of this chapter. And that's Corollary 1 and Corollary 2 from Euler's formula. We have one more corollary to discuss in another video.